Hello everyone, this is Ramon Mars, and today we're looking at IB Physics Chapter 2, Subtopic 3, Work, Energy, and Power. In this video, we're going to talk about work, Hooke's law, elastic potential energy, kinetic energy, gravitational potential energy, conservation of energy, power, and efficiency. Work is defined as force times displacement over which the force acts. If we put in the formula, that will be work times force times displacement. W equals Fs. For example, if you apply a force on an object and that object moves a displacement of s, the work done by you would equal to the magnitude of the force that you did times the displacement. The units of work are units of force times distance, newtons times meters. For convenience, we call that unit a joule, in honor of a physicist by that name. However, if the force that you're applying on an object is not parallel to the displacement of that object, the formula of work has a minor correction. We add, because they're vectors, both displacement and force, we have to, if they're not parallel, there's a certain angle between them, which here we'll define theta as angle between F and S. So the new formula for work would have to be work equals force times distance cosine theta. The first formula we used can be used for work done by constant force when theta equals 0, meaning when objects are parallel. This can be done because if theta is 0, cosine theta would equal to 1, so we can just ignore it altogether. So let's practice. Find the work done by the force of 25 newtons in displacing a box 15 meters if the force and displacement are A. parallel, B. anti-parallel, and C. at 30 degrees angle. So at A, we just when they're parallel, that means the angle between them is 0. So that would give us final work done of 380 joules. Situation B, anti-parallel means the angle is 180. They're parallel, but they're in opposite directions. So by plugging in 25 as force and 15 as displacement, and 180 degrees as theta, we get negative 380 joules as our work done. In situation B, our angle is 30 theta, and our final work would have to be 320 joules. Hooke's law. Let's imagine there is a spring which has object with a block with certain mass. The spring is not contracted or retracted, it's in its rest position, and that rest position is x equals 0. If we move this block on a spring a certain distance to the right on the x-plane, spring will create a force that's towards its initial position of x equals 0. This can be called a spring force. And similarly, if we move the block on the left of its initial position, the force made by the spring will be in the opposite direction, to the right, towards its initial position. This behavior of a spring can be set as force equals to negative Ks. Negative K is a constant. The minus sign gives the force the correct direction, which is opposite direction of displacement s, as we saw on the demonstration above. If you move the spring to, if you push the spring to the left, the force is to the right, and vice versa. Since F is in newtons and S is in meters, the unit of spring constant, which is denoted as K, the units are N per meters, newtons per meters. Let's look at an example of Hooke's law. A force versus displacement plot for a spring is shown. Find the work done by you if you displace the spring from 0 to 40 millimeters. On this plot, we can see that the spring force is displayed by the green line. We can ignore the quadrants where displacement is negative, as in the situation they say that we moved it from 0 to 40. There we can see that the force is negative because, as implied by the Hooke's law, the force is in the opposite direction and hence has the opposite sign of the displacement. However, in this situation, we need to find the work that's done by you, or by the person who's displacing the spring, meaning that this force will be same magnitude but opposite direction, meaning force will not be negative, it will be positive, as denoted by the red line on the plot. The area under the force versus displacement graph represents the work done by that force, because work equals force times displacement. The area that we need to find is from 0 millimeters to 40 millimeters. So the area equals to half base times height. In our situation, the base would be 40 and height will be 20, as you can see on the graph with the shaded red triangle. So our final area will be 0.4. Since area equals the work will the person does to displace the spring will equal to 0.4 joules. Now let's talk about elastic potential energy. We equate the work done in deforming the spring that we just found, having a spring constant of K and displacement delta x, to the energy, which we denote by EP, stored in that spring. If the deformed spring is released, it will go back to its relaxed dimension, or going to its initial position, releasing all of its stored up energy. This is why EP is called potential energy. This potential energy has a formula which equals half K delta x squared, where delta x is the displacement, K is spring constant, and EP is elastic potential energy. As we learned, the area under the force displacement graph gives the work done by the force during the displacement. So from force equals Ks and area equals half base times height, we obtain potential energy equals work, which equals to area under the graph, which is half displacement, which is the base, times height, which is the force. And since we know that the force of a spring is Ks, this can be simply put as half SKS, or half Ks squared, or as we see it in the box above, half K delta x squared. And this is the area that would let us determine the potential energy of the spring based on its displacement. Now let's talk about kinetic energy. Kinetic energy, denoted by EK, is the energy of motion, meaning anything that has motion has kinetic energy. This formula can be found in the This kinetic energy can be defined as half times mass of the object times velocity of the object squared. Units of kinetic energy will be, well, let's do an example. Use energy to find the work done by the brakes in bringing a 730 kilogram smart car to rest in 80 meters if its starting speed is 32 meters per second. So first of all, we need to define our final kinetic energy. Our final kinetic energy equals to half mv squared. So since we know that it has to come to a rest, velocity would have final velocity is 0, meaning final kinetic energy is also 0 joules. Our initial kinetic energy is half mu squared, where u is 32 meters. M is 730, which will give us initial kinetic energy of 370,000 joules. So the change in kinetic energy would be final kinetic energy minus initial, which will result in negative 370,000 joules. That will be our change in kinetic energy. And from the previous slide, we know that the work done in order to make that change in kinetic energy happen would have to be equal to that change in kinetic energy, which is 370,000 joules, which would be negative 370,000 joules. Gravitational potential energy is denoted as change in EP, is energy due to the position of a weight. In physics, we use EP as to define potential energy, and it's not specific to gravitational or spring elastic potential energy. So be aware when using different formulas to not mix up what is the AP referring to. Imagine lifting an object with a mass m to a height delta h and then letting it go. It will fall and speed up, gaining kinetic energy as it falls. Since the lift constitutes work against gravity, or the weight of the ball, we have work as that equals to force times displacement cosine theta. Theta in the situation is 0 as force and displacement are in the same direction. Force in the situation is a weight, which is denoted as mg, and the displacement from this situation we know is delta h, which gives us work equals mg delta h, which is the formula for gravitational potential energy. So let's practice. Consider a crane which lifts 2,000 kilogram weight 18 meters above its original resting place. First, what is the change in gravitational potential energy of the weight, and how much work does the crane do? So let's solve A first. The change in gravitational potential energy, as defined earlier, is mg delta h, and plugging in 2000 for mass, 10 for gravity, and 18 as change in height, which would leave us with 360,000 joules. Now we need to find how much work the crane does. In order to do that, we need to find the force done by gravity, or the weight, which would equal to mg, which would give us 20,000 newtons upwards. The displacement we know from the situation is 18 meters upwards, which we can use to find work as 360,000 joules, which means that change in gravitational potential energy and work done against weight are equal.